With this new material, we could generate energy directly from the ocean and make ships unsinkable. And no, the researchers at the University of Rochester aren't using any paint, wax or anything like that. More than 100 years after the Titanic, researchers have now modified metal so that it no longer sinks, even when it's severely damaged. This could completely revolutionize how we build ships or our coastal protection. But it could also be used to generate energy directly from the ocean. Today we will explore how this works and why nature holds the key for this innovation. And with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps, and in Germany we say Los geht's! The sinking of the Titanic happened over 100 years ago, even before World War I. But somehow it's still very present in our society and continues to have an impact to this day. The Titanic led to the first SOLAS Convention, which stands for Safety of Life at Sea. This is essentially the safety standard for the world's oceans. And since then, massive research has been conducted on ship safety every year. But research isn't limited to ships. It extends to everything that meant to float on the sea, whether it's offshore wind turbines, floating photovoltaic systems, or massive infrastructure projects. We need structures that are stable, scalable, and extremely robust on the water. Before we look at the solution, let's briefly cover a few basics. So why do ships float in the first place? Well, objects experience an upward push in water called buoyancy. You're familiar with this from everyday life. This buoyant force counteracts the object's weight, and it is always exactly equal to the weight of the displaced water. So if an object displaces enough water so that the buoyant force balances its own weight, it floats. And this applies, for example, when the density of an object is less than the density of water. If the buoyant force is even greater than the ship's weight, the ship can carry as much cargo as it needs until the forces are balanced again. But the new material isn't just hollow, it also has a second trick up its sleeve: surface tension. To make the metal float, the researchers from New York are using what's known as superhydrophobicity. That basically just means total fear of water. You might be familiar with this from the lotus effect. Water droplets simply roll off the leaf without wetting the surface. In science, this is measured using the contact angle. Imagine a water droplet hitting a surface. If it spreads out flat like a pancake, the angle is small. But if it rolls off like a marble, the angle is large. At 150 degrees or higher, we are talking about superhydrophobicity. And the new metal now achieves a whopping 158 degrees. So water barely touches the metal at all. The researchers at the University of Rochester aren't using any paint, wax or anything like that. Instead, they are altering the structure of the metal itself. To do this, the aluminum tubes are placed in a bath of copper chloride solution for 15 minutes. As a result, microscopic indentations, so-called pits, form on the metal, and any remaining disturbing particles are then removed using ultrasound. Under the microscope, the metal now resembles a rugged mountain landscape made up of micro and nanostructures. Now that the physical structure has been created, or rather modified, the surface energy is also being reduced in order to drastically lower water wettability even further. This was first tested with stearic acid. However, to ensure it also works in seawater, PDMS, a type of silicon polymer, was later used. It is vaporized in an oven at 300 degrees and settles as a wafer-thin layer on the rough structure. This treatment ultimately results in a contact angle of approximately 158 degrees, making it a superhydrophobic surface. And this combination ultimately leads to the entrapment of stable layer of air known as plastron. And the thing is, the principle itself isn't entirely new. In 2019, initial experiments were already conducted using two superhydrophobic discs. The problem, however, was that if you tilted them past a certain angle, the air simply escaped and the structure collapsed. But that has now been bypassed. So instead of the plates, the researchers are now using small tubes. And the inner surface of these tubes have been treated, as I explained earlier. This creates a stable air bubble inside the tubes that physically blocks the water. But the key feature is something else: a partition in the middle of the tube. Thanks to that, the air bubble remains trapped no matter how rough the waves are or whether the tube is submerged vertically. The geometry forces the air to stay inside. And with this innovation, they have now achieved real success. The researchers were able to demonstrate that the tube structure remains unsinkable even when subjected to massive mechanical damage. In the test, they drilled up to 15 holes in the tubes and the water didn't get in even then. And even in long-term tests with highly concentrated salt water and simulated wave action, the pipes kept working perfectly. They tested over periods that, according to the paper's calculations, correspond to about 3 months on the open sea. What is particularly noteworthy is that, unlike conventional marine materials, there were no signs of biofouling, that is, the unwanted growth of organisms. But of course, it must be noted that all of this has so far only been tested in a model. Whether this would also be the case in the real ocean would have to be tested again. If everything goes to plan, this will definitely be a game changer. It is even possible to construct rafts or platforms with an enormous load-bearing capacity by connecting several tubes together. Specifically, these structures can support nearly 3 times their own weight at the surface. And last but not least, an initial prototype has demonstrated the potential to generate energy from wave motion. To do this, they use the kinetic energy of the waves to generate electricity directly via electromagnetic induction. Okay, this sounds really great, but despite all the positive news, we need to talk about the challenges, as I do in every of my videos in the part I call the big hurdle. Before we do that, please hit subscribe and activate notifications so you don't miss any more videos and support this channel for free. Okay, let's start with a big hurdle. Perhaps the biggest hurdle right at the beginning is the technology has one major limiting factor, and that is the diameter. There's both an upper and lower limit for the diameter of the tubes. If the inner diameter becomes too large, roughly between 5.34 and 6.43 millimeters, the surface tension can't withstand the hydrostatic pressure anymore. In this case, the water gets past the barrier, seeps in, and the stabilizing air bubble escapes. On the other hand, if the diameter is too small, less than 0.88 millimeters, there simply won't be enough air volume to support the weight of the metal used. And for me, maybe the biggest hurdle on top of that is the whole process is quite maintenance intensive. To keep the superhydrophobic properties at the opening stable over the long term, it might be necessary to perform a follow-up treatment once a year. Like I said, we still have to find out. And then there's a depth factor. Since the principle is based on trapping air, the hydrostatic pressure becomes so high at a certain depth that the water is forced into the pores and displaces the air. This means the technology is primarily designed for applications at the water surface, but since that's the main focus anyway, I don't find that so relevant for me. It is like a very small hurdle. And of course, I also have to mention that at this point, the structure in the current presentation is very simplified, especially when it comes to the materials used, which theoretically couldn't be used for ships at all. Like, this is a test in laboratory. Okay, so we are not going to suddenly see cruise ships tomorrow that will never sink again. Surprise, surprise. The system, or rather the experimental setup, is still far too simple for that and takes far too few factors into account. But for the next generation of, for example, offshore installations, autonomous research buoys, or unsinkable rescue platforms, this could be generally relevant. And that's exactly where the researchers from New York see the big potential. And now to you, where do you think these unsinkable structures could be used? And also, what is your opinion on the whole innovations? Please let me know in the comments. By the way, thank you for all these great comments here under the videos. I really love it. And be sure to check out this video about new energy production. It's a very interesting topic. And I would say, see you next time, or auf Wiedersehen, as we say in Germany, your Jacob.